disease. And there's an easy way to tell this. If most of the males in the pedigree affected, if they're mostly males, it's probably X-linked. If you remember, females often end up being carriers of X-linked traits. Males only need one copy, so they get it. Okay? If it's 50-50, men and women both get it, then it's an autosomal trait. Okay? So how about that one? That's a whopper. This is actually the pedigree chart for the royal family of England. See if you can find King Henry on there. Or see if you can explain why Louis, the Grand Duke of Hesse, had a son who then married Beatrice, who you can see that dot in there, was a carrier. And this pedigree actually tracks a disease called hemophilia. And that is a disease that causes excessive bleeding, the inability of blood to clot. So let's come back to that. When we look at these pedigree charts, that's first thing, is the trait autosomal or X-linked. If you look at this chart, you'll notice that there is a female with the trait. There's a male with the trait. There's another female, and there is a male. So would you say that this is autosomal or X-linked? What do you think? Autosomal X-linked. And so if you go back to those rules, remember, if we said if both males, males and females get it, then it's an autosomal trait. Okay? So if this were on a quiz, you would pick A, autosomal, or whatever letter was autosomal. If you look at this, would you say that this pedigree chart indicates an autosomal or sex-linked trait? So you go through. If you notice, Queen Victoria, she's actually a circle with a dot. She was a carrier. Alice is a female. She was a carrier. Irene, Princess of Henry, she was a carrier. Carrier, 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 carrier. Interesting, huh? None of the females actually have the disease. Yet, if you look at Leopold and Maurice and Frederick and Henry, and if you look at, I don't know who that is, Prince Sigmund of Prussia, you will notice that all of the individuals that actually have the disease are males. And since predominantly males have it, we would say that this trait, hemophilia, is sex-linked. We know that gene's on the X chromosome. So, another example of a sex-linked trait or X-linked trait is male pattern baldness. And in fact, you see this more frequently in males. Fellas, I can tell you that if your mother's father, your grandfather on your mother's side, is bald, then there's a 50% chance then you will be. It's not a guarantee, but you inherit this gene from your mother. Okay, if you're a guy, you got a Y chromosome from dad, no gene on that. Another example of a sex-linked trait is color blindness. And if you look at the first box here, if you can read a number in the middle of that box, then you are not colorblind. And if you can read the number in this box, then you are not colorblind. But if you can't read those numbers, then you are in fact red, green, colorblind. And you can look these up. There's lots of tests for this. But again, color blindness is on the X chromosome. It's sex-linked. So how do we determine if a trait is dominant or recessive? That's a bit more difficult. And so we have to go into this and we have to look at the generations. If a disorder is dominant, one of the parents must have the disorder. Dominant traits can't be covered up. You can't be a carrier of a dominant trait. Okay? If the disorder is recessive, then there can be carriers. You can have both parents be completely normal, but pass that trait on to their children. Let's take a look at that. Okay? So an example, you would look at a chart like this. You would say, is this dominant or recessive? And as you can see, there are individuals in each generation with the trait. Okay, so we would say, therefore, that this is a dominant trait. And we can sort of start to figure this out, and this is a really good thing to do. If an individual is normal, let's say that the trait is big A, little a, right? We know big A is going to be our dominant trait. Little a is going to be our recessive trait. If an individual is normal, we know that they must be little a, little a. Because if they even have one gene, then they'll get the trait. Now, look here. This cross right here, they actually have an offspring that's normal, that has to be little a, little a. Now, what that means is they got a little a from one parent, and this parent also has to have a little a. So what I've done is, I know this person has one big A. They have the trait, but I know that they're heterozygous, big A, little a, because they have offspring of both phenotypes, normal and with the trait. Most likely, this individual got a little a from the parent with both and is also heterozygous. And this is the process of determining the genotype by analyzing the pedigree. So lots of examples of dominant traits that can be inherited. Achondroplasia is actually a dominant trait. And we know dominant doesn't mean better. Dominant doesn't mean you get it more. Dominant just means in the case of having, one of each, in this case, the person would get achondroplasia, also known as dwarfism. And there are actually a number of genetic disorders that can cause dwarfism. Achondroplasia is the most prevalent. The only way to actually be normal is to have two recessive genes. Another example of a dominant trait is polydactyly, right? So if I were going to use the letter P to symbolize the allele for polydactyly, would I use the capital P or lowercase p? And since polydactyly is dominant, I would use a capital P for polydactyly, lowercase p for 5 fingers. Anytime you see a pedigree chart where individuals in every generation have the trait, then more often than not, it's a dominant trait. Okay? Huntington's disease. Again, if you look at the pedigree, has it. Huntington's disease causes a degradation of brain tissue. This is a normal brain. This is the brain of a person with Huntington's. Again, a dominant trait. But what about recessive traits? So if we look at here, dominant or recessive, we would say, in this case, that this pedigree chart represents a recessive trait. So here are individuals with this trait. But look at all the parents. They're normal. And so what we tend to say is that recessive traits skip generations. And in the case of two parents who are both normal, maybe they're big A, little a, big A, little a. Now I know that they're both heterozygous, right? They have one of each gene, but they had an offspring that if it's a recessive trait, the only way to get it is to be homozygous recessive, little a, right? I know that they are both what we would call carriers. So, lots of examples. Every once in a while, you will see a pedigree chart that actually has a half-shaded symbol to represent an individual that is a carrier, if they know. But I find it's easier to actually just write the letters in the symbols, whatever the symbol is. Lots of examples of recessive traits. This is actually the Ehlers-Danlos syndrome, is that sort of elastic skin syndrome. It's actually the absence of collagen, connective tissue in a person, so that their joints and their skin doesn't totally connect. Recessive, class is about to start, so I'm going to end this bad boy. Lots of examples of cool diseases for you to look at. You can pause that and go back to it if you want. And then this is the end.